in order to follow along with this example problem, you're going to need to download the document that is linked above this video. All right, so we've talked about using bar charts to chart where energy is based on where our object is in space, and so how much energy an object has before and after a move. And so I wanted to show you guys how that's actually going to be really useful for us. Because up until now, what we've been showing with the bar charts is something that could have been easy enough to just solve without them. Okay, but here's where the bar charts are going to start becoming very useful for us. Okay, and so I'm going to take you through an example calculation, and then you'll have 3 more in this document that you'll get to work through and practice. All right, so first thing we're going to have to do is read our problem. And it says, determine the final velocity of a medicine ball that is dropped from a height of 7 meters. Okay, so we've got an initial height of our object. So first thing we're going to go ahead and do is we're going to draw what is happening here. And so I am going to draw a little medicine ball. And I know that that medicine ball is 7 meters above the earth. Okay. Whenever I am drawing my object, I am always going to include the earth. If I don't include the earth, I can't talk about potential energy, because potential energy is based on the earth's gravity. And so I'm always going to be drawing in the earth. All right. We are dropping this ball from rest, and so it is not moving. Okay. Then you'll notice that there's this little box here that says energy transfer external work. Okay. For right now, we are not going to be talking about outside forces, but if there was friction or air resistance and we were going to take that stuff into account, that's when we would use this box, and we're going to talk about that in the future, okay? So right now, you're going to ignore the box, but it's there for when we have an outside force that we talk about. All right, so now our medicine ball is going to be reaching the earth. Okay, and so I'm going to draw, again, the medicine ball. Now it's on the earth, and I'm going to add the earth in again. Okay, and so now we don't know the velocity, but we do know that it's going downwards because it was going towards the earth. All right, and we know that our height is now going to be 0 meters because our medicine ball has reached the earth. All right, so then we're going to start working on our energy bar chart. And so I'm just filling in what types of energy we could have. So we could have some potential energy. We could have some kinetic energy at the beginning. Right? We could have some potential energy at the end and some kinetic energy at the end. And so what I'm going to do is I'm going to look back up to the diagram, and I'm going to ask myself, are there any zeros? And so right off the bat, anytime that there is no velocity, I know there is no kinetic energy. And since our initial velocity was 0, I'm going to go ahead and say there is no or 0 joules of kinetic energy at the beginning. Okay. And then I'm going to look over at the end. Are there any zeros? Sure enough, there's a height of 0. I know that anytime there's a height of 0, 0 joules is my potential energy. So I can fill those right in. Okay. Now, I know I'm going to have some kinetic energy, 7 meters tall, so I'm just going to estimate, let's say that's about 4 bars worth of energy. And since I know my energy has to be conserved, that means I must have about 4 bars of kinetic energy at the end. All right, so that's my energy bar chart. Now it's asking me to write a mathematical statement that relates initial energy, work, and final energy of the system. So what I'm going to do here is I'm going to go up here and I'm going to cross out anything that was 0. So initial kinetic energy was 0. Final potential energy was 0. Now I'm going to come back down here and I'm going to just write what's left. So what's left is I have potential energy initial. Then I have my equal sign right here. And I have kinetic energy final. All right, so now I've got an equation. Now it's time to actually solve. So what were we really looking for? We wanted to know, we wanted to know the final velocity. All right. So then we're going to go ahead and any numbers that we already know, we're going to write in here. And so I know that we have an initial height of 7 meters because that's on the left side of my diagram. On the right side, I have a question mark for velocity. That's my unknown. I'm going to go ahead and add that. Okay. I also know that gravity is going to be 9.8 meters per second squared. All right, now I'm going to go ahead and plug in my equation. So potential energy at the beginning is equal to kinetic energy at the end. Instead of potential energy, I'm going to plug in my potential energy equation using an I for height because this is our initial height. And then same thing with kinetic energy using an F for velocity because it's our final velocity. All right, so now I'm looking at my equation and I'm looking at everything that I know and I'm noticing that I don't know mass. All right, so here I might be stuck. But there's this really cool thing. Because mass is in both terms, it's on both sides, I can cancel it. All right, here's how I would do that. I could say we're going to divide by mass over here. And anything I do to one side, I have to do to the other. So because I divided by mass on the right side of my equation, those cancel out. And guess what? Those ones cancel out as well. And so that leaves me with gravity times initial height equals 1/2 times velocity final squared. All right, now it's time to go ahead and add in my numbers. So I know gravity is 9.8 meters per second squared here on Earth. I know that my medicine ball is starting 7 meters high. All right, we're going to keep in that 1/2, and we are looking for that final velocity. All right, so then we're going to pull out a calculator. We're going to say 9.8 times 7. What does that give us? 68.6. All right, and that's going to be meters squared over seconds squared equals 1/2 times velocity final squared. Now I need to get rid of this 1/2, so I am going to go ahead and I'm going to multiply both sides by 2. All right, and so that is going to give me 137.2. And then this 1/2 and this 2 are going to cancel, and so that leaves me with velocity final squared. All right, going to go ahead and square root both sides of the equal sign. Square root of 137.2 is going to give us 11.7. And that is our final velocity. All right, so because we were able to track our energy above, we were able to really simplify this equation. Instead of having both potential and kinetic energy at the beginning and then finding out that one was 0, we could take it out right from the start in order to really simplify that math for us. All right, I hope you guys enjoyed this. There are some more problems in this document, 3 more problems that I'd like you guys to work through, and then you'll be submitting them later on today. All right, please reach out if you have any questions. You can reach me via WebEx between 9 and 11 a.m. After that, I will try to respond as I see your messages. However, I will not be responding immediately. Thank you.